are 3 and -3. Those numbers are going to multiply to -9, but they'll also add to 0. So those two numbers, 3 and -3, that's just telling me I can factor this as x plus 3 times x minus 3. And if you want to check if that's correct, you can always re-multiply this, right? So if you re-multiply, x times x is x squared. We get x times -3, so -3x. We get a 3 times an x, so plus 3x. And then finally, 3 times -3, which is -9. So it's going to turn out that here the -3x and 3x cancel, and you're left with x squared minus 9. So all we're doing is we're rewriting this, x squared minus 9, we're rewriting it as x plus 3, x minus 3. This is factoring. What we're doing is we're breaking this thing up into its factors. We're breaking it up into its factors, just like you could break up 12 into 6 and 2, because 6 times 2 is 12. You can break up x squared minus 9 into x plus 3 and x minus 3 because x plus 3 times x minus 3 equals x squared minus 9. So it's the same concept of breaking up a number into its factors. We're just breaking up an expression, a higher order expression into its factors. All right. So we have kind of our first chunk. I'm just going to look at the second chunk here now. So again, it's the same exact concept because we're factoring quadratics. If you're factoring quadratics, kind of the first thing you'd want to look to is what are two numbers that multiply to AC and add to B. So here in this example, A is 1, C is 4, so that means AC is 4, right? 1 times 4 is 4, and then B is -5. So we need two numbers that multiply to +4 and add to -5. So take a sec, pause it, get those numbers. Looks like the number should be -4 and -1, right? Because -4 times -1 is +4. -4 plus -1 is -5. So we're going to factor this as x minus 4 times x minus 1. And you'll notice that the two numbers we came up with, we can just slap them right into our linear factors. We did that in both examples here. That's going to work as long as A equals 1. That's going to work as long as A equals 1. See how A equals 1, A equals 1. So I'm allowed to just get these two numbers that multiply to AC and add to B, and I can just slap them in like I did here, and like I did here. So what you're going to get as a final answer is a little weird. So the first thing we did is we rewrote x squared minus 9 as x plus 3, x minus 3, right? And we rewrote the first quadratic, x squared minus 5x plus 4, as x minus 4 times x minus 1. So that's going to be your complete answer here. And what's going to happen is if you want to check this in any order, actually, you could multiply all of these terms together and you should get your same original kind of answer. And if you multiply these together, you should get the same as if you multiply all of this. So we're not changing anything. We're just rewriting it there. Got it. Awesome. All right. So we're at the next question here. So again, we're trying to factor this. So we're trying to take this polynomial, and it's a higher degree function here. This is a 4th degree function. It's a quartic. And what we're trying to do is write this as a bunch of linear factors being multiplied. So, and this is not the answer. I'm just saying, for example, maybe x plus 2 times x minus 8 times like x plus 1. You might see, a bunch of linear terms being multiplied. So can we break this down into a bunch of linear terms being multiplied? So let's see if we can do that. So take a second, pause, try to do this on your own. The first thing I would say is I see common factors. So I see a 5, I see a 20, and I see a 20. So from all of these numbers, I can pull out a 5. I can pull a 5 out of all of these numbers really cleanly. And I can also pull x squared out. All of these terms have x squared. So I'm actually going to pull out the greatest common factor of all of these terms. The greatest common factor is 5x squared. So I'm going to pull 5x squared out of every single term and rewrite it like this. So I get 5x squared times, and kind of what I do is I ask myself 5x squared times what is going to give me 5x to the fourth? Well, the number I need is 1 because 5 times 1 is 5. And I'm just going to actually multiply this by x squared. 5x squared times x squared is 5x to the fourth. Add the exponents. Minus, so 5x squared times what is going to give me negative 20x cubed? 5x squared times what is going to give me negative 20x cubed? It's going to be negative 4x. The 5 and the negative 4 give me the negative 20, and the x squared and x give me x to the third because I add the exponents. And the exponent here is a 1. It's invisible. I don't write it, but it is a 1. And then finally, I'm going to have plus 4. The plus 4, why is it plus 4? 4 times 5x squared is 20x squared. So now what I've done is I pulled out my greatest common factor. That makes this a lot easier because right now I can factor this just like in the last examples. I need two numbers that multiply to AC. So A is 1, C is 4. Ooh, 4. So AC is 4. AC means A times C. And then they need to add to B. So I need two numbers that multiply to positive 4 and add to negative 4. Take a sec, come up with those numbers. We should get negative 2 and negative 2. I believe we get negative 2 twice. So what we're going to do is I'm just going to rewrite this. Right, all I did from here to here is rewrite. I just pulled out the 5x squared. And now I'm going to rewrite again. I'm only going to rewrite what's in parentheses. So I'm going to keep the 5x squared, and I'll actually just put this as my answer. I'll keep the 5x squared to the second power. So I keep that, and now I'm going to rewrite the quadratic as x minus 2 times x minus 2. And remember, the reason I'm doing that is because I needed to find two numbers that multiply to positive 4. So these two numbers multiply to positive 4, and they add to negative 4. Those two numbers are negative 2 and negative 2. They multiply to the positive 4, they add to the negative 4. So I can factor this expression as x minus 2 squared. So I could have also written this as x minus 2 squared. But what I've written here is the exact same thing mathematically. So hopefully they give that to me, and they do. All right, let's take a look at the next one. Okay. So in this question here, again, we need to factor. So we're trying to use some strategies that we have, from previous math to rewrite this whole expression as a product of linear factors. So we're trying to just have a bunch of things multiplied. Right now, all these things are being added and subtracted. And again, the whole reason you factor is to find the zeros of the function, to find the roots of the equation. So what I'm looking at here, this is not a quadratic, right? So you cannot use the typical quadratic strategies because this is raised to the third power. So we're going to need to use some other strategies. So one thing that I'm looking at when I have four terms like this, what I'm really looking at is, do I have a common ratio? Do I have a common ratio? Because if I have a common ratio between the first two and the last two, I can use the strategy called grouping. I can use grouping as a strategy. So take a second and think, is there a common ratio between these two sets of numbers? To me, it looks like the answer is yes. It looks like I have a common ratio of 7. So, right, if I go from 1 to 7, this second term is 7 times as big as the first term, right? 7 to 1. Same concept here. 35 is 7 times as big as 5. So why does this help us? This just lets us use the grouping strategy. So let's do this. So we're going to group the first two together because these have a ratio of 7 to 1, and these also have that same ratio of 7 to 1. So I'm just going to kind of clear stuff here. So for these first two terms, all I'm going to do is pull out whatever I can. I'm going to pull out the greatest common factor. So the greatest common factor between these two, I can't pull out any numbers because this only has a 1, but I can pull out x squared. So I'll pull out x squared. So when I say pull out x squared, right, kind of like the last problem, I'm sort of undistributing the x squared, and I'm left with x plus 7. How do I know I'm left with x plus 7? I think of it this way. X squared times what is going to give me x cubed? And the answer is x. X squared times x is x cubed. And then x squared times 7 is 7x squared. So this expression, if I write this, that's literally the exact same thing as writing this. right? So notice that I didn't change anything. I just wrote it in a different way. So that was kind of our first step. All right. And now I need to deal with these second two terms. So the trick here with grouping is I need to get x plus 7 again. So what I'm going to do, I know I need x plus 7 in here. You can kind of cheat like that a little bit, but don't still check the math. You still have to check the math. You cannot just fully cheat with this. But I will tell you, I do cheat a little bit. So I cheat at the start. So I know that if grouping is going to work, I need to have x plus 7 here as well. So now the question is, what would need to go outside of this to give me x plus 7 in the middle? And I will admit, this is a little of a backwards way of thinking of it. And I'll do it the other way as well. But now let's think, what times x is negative 5x? Well, that's just negative 5. And negative 5 times 7, that's negative 35. So it looks like this whole deal here, right? This whole deal here, if I redistribute it, I just get negative 5x minus 35. That's exactly what I had before, minus 5x minus 35. So all I did is I rewrote it. I rewrote negative 5x minus 35 as negative 5 times x plus 7. So hopefully you can see how these two things are the exact same thing, just written differently. So now what this allows you to do, and this is where grouping becomes a little weird. This is the weird part of grouping. So with grouping, we're going to rewrite this, and let's talk through how we're going to rewrite it. So what we're going to do is a little weird. We're going to look at this term here and this term here and say, oh my goodness, there's a common factor of x plus 7. This term and this term both have x plus 7. So let's pull that out. Let's pull out x plus 7. And that might seem a little weird, but mathematically that does work. It's a common factor. It's being multiplied. Let's unmultiply it. So let's pull it out, right? And what's left? If you pull out the common factor of x plus 7, what's left is x squared minus 5. And again, this is very weird, but there's a couple of ways I could prove that this works. So if you redistribute the x plus 7, that's one way to think about it. I would just get x squared times x plus 7 minus 5 times x plus 7. And maybe that is the best way to kind of see it, is that this thing here, right, is the exact same as this thing here. Right, so you can think of it in different ways. Again, I'm just writing it in different ways. But when we're looking to factor, this is kind of more what we're looking for. This is kind of more the form we're looking for. Now, let's talk about this. So if I put this in as an answer, x plus 7 times x squared minus 5. X plus 7 times x squared minus 5. And you might be asking yourself, why do I not factor the quadratic here? And that is a great question. Once I get this written in correctly, x squared minus 5. So why do I not factor this? I could certainly try, and I think that is the right instinct to try to factor this further. The problem is you're not going to find two numbers that multiply to negative 5 and add to 0. That would just be the square root of 5. So you're going to end up with x plus the square root of 5, x minus the square root of 5. But this is going to give you square roots, right? This doesn't look very clean. If I were to factor this further with square roots, it actually doesn't make things simpler in any way. And a lot of what we're doing is just trying to make things simpler and easier to work with. So this is actually a really finalized, simplified way to look at things because this lets you solve for the roots, right? If you set this equal to 0, what are the solutions to this equation? You would set x plus 7 equal to 0. One of the solutions is negative 7. So if I plug in negative 7 here, I'll get 0. And my other solutions, I can just set this equal to 0. X squared minus 5 equals 0. So that means x squared equals 5. If I add 5 to both sides, so that means x equals, I'd have to take a square root of both sides. So plus or minus the square root of 5. So this is why this answer is satisfactory, because once you take this big polynomial and break it and factor it like this, you can find all of the solutions just by this factorization. So you can find your solutions are negative 7 and plus or minus the square root of 5. So this is fully factored because it lets you find the solutions. You could try to factor the quadratic further, but you're not going to get anywhere clean. And this is should be an acceptable answer. Yes.